Today's lesson is about factoring expressions using the distributive property. So our learning target is I can factor expressions by applying the distributive property. The distributive property is not something new in 7th grade. It's something that's been taught in elementary school and in 6th grade. And in my most recent lesson, I had another lesson on the distributive property, but it had to do with expanding expressions. And in that lesson, we used the area models that we'll be using in this same lesson. So if you didn't check out my expanding expressions lesson, that might be a great idea before heading into this lesson. So we're going to be exploring factoring expressions using area models to kind of help us think about how we work backwards. So essentially factoring means that we're undistributing. We are working backwards, meaning that if you look at this big rectangle, there's an expression inside that says 12x plus 18, and that represents the area of the big rectangle. So thinking like just kind of pausing, like what do you notice? What do you wonder? You can pause the video. But some things that you might have thought about are that both terms are positive. Maybe you notice one term has a variable, the other term does not. Maybe you notice 12 and 18 share some common factors. They're both even numbers. A couple different things. There's no right or wrong answer, just kind of getting you thinking about what those terms have in common. So another question that you might have come up with is, okay, so that's the area. What's the actual dimensions of this rectangle? Like what's the height? What's the width? So in the next question, it says the area of the rectangle could also come from the area of two smaller rectangles side by side. Something that we talked about in the last lesson, that we could take the area of a big rectangle or kind of chop it into two smaller rectangles. And sometimes that makes our problem a little bit easier to manage or to think about. So when I scroll down, it shows how this big rectangle that had an area of 12x plus 18 was split into two smaller rectangles, where the first rectangle had an area of 12x, and we don't know what the height is, and we don't know what the width is. The second rectangle has an area of 18. So 18 equals a shared height times, whoops, let me make that smaller, times an unknown width. So this is area 2. So when I say they share a height, hopefully you can see from the picture here that from here to here is going to be the same distance from here to here and the same distance from here to here, right? Just thinking about the properties of a rectangle. So all these heights are the same. So if we know these are the areas, we're trying to find a height that would be a number that essentially goes into both 12x and 18. So we're looking at this height right here and how this height has to be the same. Notice this says width 1 and width 2, meaning that these widths can be different lengths, but their heights actually have to be the same in order for this, in order to factor this to be able to take the big rectangle and kind of split it into two smaller rectangles, you need to have a shared height. So right now, when you're looking at 12 and 18, we're looking for essentially a number that goes into both 12 and 18. When we're looking for a number that goes into another number, that's called factoring or finding the factors, which is a standard in previous grade levels. So when I look, I can go ahead and kind of list my factors of 12 and 18. So 1 times 12, 2 times 6, and then we have 3 times 4. So those are the factors of 12. And with 18, we have factors 1 and 18, 2 and 9, and 3 and 6. So when we look, we see that there's actually a lot of factors shared between them, right? They're both divisible by 2, 3, and 6. So you might be asking, like, which one do we pick? What could the height be? And in all honesty, the height could be 2, it could be 3, it could be 6. We don't know what x is yet. So in terms of this problem, it really could be any one of those factors. So let's kind of play around this idea of like what would the other width be if the height was 2, for example. So let's say the height was 2. What might the width be? So when I'm looking at the height, if I'm looking at just the green rectangle, I'm looking for essentially 2 times what would give me 12x. And that would be 6x. 2 times 6x gives me 12x. And then I'm thinking 2 times what would give me 18. So 2 times 9 would give me 18. So question 4 says, can you write the area of the big rectangle as height times width 1 plus width 2? Meaning that the height of the rectangle is 2, and then I would write the width as 6x plus 9, because the width from here to here is 6x, and then the width from here to here is 9. And so if I add those two numbers together, that would be the total length on the long side of the rectangle. Now, I'm going to go back and I'm going to essentially erase them. And I want us to think about, what if the height was 3? So if the height was 3, then how would that affect our widths? So I'm looking at 3 times what would give me 12x. That would be 4x. And then 3 times what is 18? That would be 6. So another way to write the area of the big rectangle could be 3 times 4x plus 6, the height times the total width. And then lastly, let's replace 3 with the greatest common factor, which is 6. So if the height is 6, 6 times 2x would be 12x, and then 6 times 3 would be 18. So 6 times 2x is 12x, 6 times 3 is 18. So 6 times 2x plus 3. So when you look at these 3 expressions in a row, they're all equivalent to each other, meaning that if I was to actually distribute, thinking about our last lesson, if I was to expand these expressions, I would do 2 times each of the terms inside, and I would get 2 times 6x, which is 12x, 2 times 9, which is plus 18. If I did it for each one, I would get 12x plus 18 every time. So question 5 just says, are they equivalent? Yes, we've proved that. And now you might ask, like, why did I go through all the different factors? Why did I go through 2 as a height, 3 as a height, 6 as a height? I like to show my students this to show how there's actually multiple expressions that represent the same area. There's multiple dimensions that actually would give you an area of 12x plus 18. Because x is that unknown, we still don't know, which expression necessarily is correct. What are the correct dimensions? So because we don't really know what x is and we're just trying to write equivalent expressions, when we go to factor an expression, we always pick the expression that has the greatest common factor, which would be 6. It is the largest factor that goes into both areas. Okay. If you look at the other widths, like 4x plus 6 or 6x plus 9, you can actually see that there are still common factors between 6 and 9. Okay, 6 and 9 have a common factor of 3. Look at this one, 4 and 6, they still have a common factor of 2. But when you factor out the greatest common factor, the factors are like the leftover factors that are inside, cannot be factored anymore, meaning that 2 and 3 don't share any more factors. They're both prime numbers. So there's a lot of advantages to doing this, and it especially will pay off when you get into more complex factoring and algebra. But it's important for you to be able to see how there's actually multiple expressions that are equivalent, but there's one right way to kind of to actually factor the expression, which is picking that greatest common factor. So at the bottom of my notes here, I just kind of reminded readers what the greatest common factor is and how it's important for factoring. And so don't forget that the greatest common factor is the largest number that divides two or more integers. So if we looked at the next page, I kind of have a summary similar to my expanding expressions notes to show how the sum of the areas of the smaller rectangles equal the product or the area of the big rectangle. So again, showing that in kind of general form with length and width, but then also showing it in with numbers as an example. So when we fill in the blanks here, it says, it should say, when we factor an expression, we're given the areas as a sum of the smaller rectangles and rewrite it as a product or the area of a large rectangle. So meaning that we are given those smaller areas as a sum. So this is like area 1 plus area 2. And then we're going to rewrite it as a product, meaning that we're going to take the length, the common length, and then multiply it by essentially the widths added together. So when we look at an example, my example down here with our step 1, 2, 3, if you notice one of our terms is actually negative because it's an important piece when we get in 7th grade, we're dealing with positive and negative coefficients. So it says negative 24x plus 40 equals blank. So we can do this with an area model or kind of showing how you can do it without an area model. Either one is completely fine. I personally really like the area models with this, with factoring. It helps me really keep my signs straight, and I'll kind of explain why, but I'll give you an example of how to do it both with and without. So step 1 says find the greatest common factor of all terms. And then it says if the first or leading term is negative, then the GCF is also negative. So when I'm thinking about my greatest common factors, I'm kind of ignoring the signs right now. I'm just looking at what's the largest number that goes into both 24 and 40. So I can start listing like 1 and 24. 2 times 12 is 24. 3 times 8. And then 4 times 6. And then with 40, I got 1 times 40. 2 times 20. No, 3, 4 times 10. 5 times 8. And that's about it. So when I look at greatest common factor, I kind of like to work from this side. So when I'm looking, I notice that 8 is our greatest common factor. So I'm going to write 8 down, but then I have to double check that the sign of the leading term is negative or not. So when I say leading term, that means our first term. If our first term is negative, then our GCF is also negative. So my GCF should be -8, and that's extremely important. Step 2 then says divide each term by the GCF to find the other factor or terms that go in the parentheses. So I'm essentially going to take my first term, negative 24x, okay, and I'm going to divide it by -8. So negative 24x divided by -8 would be positive 3x. And then I'm going to take the next term, however many terms there are. The next term is positive 40. Remember, always keep the sign with the term. So I have positive 40. And then I'm going to also divide that by -8. So positive 40 divided by -8 would actually be -5. So essentially what I just did here is I took this area and said -8 times 3x gives me -24x. I took the next area, which is 40, and I said -8 times -5 would give me positive 40. So again, that greatest common factor is our common factor, and then I found the other terms or the other factors that would make the other dimensions. So when you write out the factored form, I would write my GCF outside of parentheses, and then I would write essentially my other leftover factors is 3x minus 5. So this is kind of like your width 1 and your width 2. Notice that I wrote 3x minus 5. I didn't write 3x plus negative 5. We like to not have two signs next to each other. So if the second term here is positive or negative, that's going to either show that you're adding or subtracting. I kind of went into that a little bit more detail in my expanding expressions video lesson. But understanding that your positive and negative numbers can also be used as your addition or subtraction symbols. So this is how I write my final answer. So on the line, I would say that this is equivalent to also negative 8 times 3x minus 5. A great way to check your work is by expanding. So if I do negative 8 times 3x, I get negative 24x. If I do negative 8 times negative 5, I get positive 40. So I would add 40. And if you notice, those expressions check. So factoring is just undistributing. It's working backwards. So now we're going to look at some examples. We have 4 we do problems to do. And I'm going to show how to do these with the area model because I think the area model really helps with the signs. So when you look at your problems here, you notice that we're essentially given we are given the area as a sum. So every problem, the first term is the area of the first rectangle. The first term is the area of the first smaller rectangle. And then the second term is the area of like the second rectangle. So that's how I kind of start with how do I set up my area models. So your first term, again, is always going to be your area of your first smaller area. And then your second number is going to be the area of your second rectangle. And notice that I'm keeping the signs with the term. This is how you set it up. And I wanted to kind of do them all at once so you can see kind of the big picture of like we are starting with the area. We are starting with the area as a sum. Okay, we are starting with the big area and we're essentially trying to work backwards and find our dimensions. We're trying to find like what is the height, what are the two widths. So essentially this is what we're trying to find, is like kind of filling in these blanks here. What's the height? What's the shared height? What's the width? So you always want to start with your GCF, which is going to be your shared height. It's that shared number, the largest factor that goes into both. So if we look at the first problem, we see 5x and negative 15. Right away, you might realize, hey, 5 is a common factor. And you're right. 5 is the common factor that goes into 5x minus 15. I'm going to check that my first term is positive or negative. If it's positive, my GCF is positive. And then I'm going to find the other dimensions. So when I think about the other dimensions, what I'm saying is that the area of this rectangle is 5x. Okay? So I'm thinking 5 times what gives me 5x? And that would be x. So 5 times x would give me 5x. You also can essentially think about it as dividing this first term, okay, by the GCF. So 5x divided by 5 would also give me x. When you look at your second smaller rectangle, think about the same thing. So you can think about it as 5 times what would give me negative 15. So you might just know 5 times negative 3 would give me negative 15. Or you can think about it as division. So I could do negative 15 divided by 5, and that would also give me negative 3. How I write my final answer is my greatest common factor goes outside the parentheses, and then the width, the total width is what goes in the parentheses. So that would be x minus 3. So kind of showing you how you can do it with or without the area model. Okay, we look at the next example. We have negative 4c plus 4. So I look at negative 4 and 4. Right away, they're matching numbers. So you can realize that 4 would be the greatest common factor here. My leading term, my first term is negative, so my greatest common factor is actually going to be negative 4. So then when I'm filling in the blanks, I'm thinking negative 4 times what would give me negative 4c? This would be just negative 4 times c would give me negative 4c. If I showed it as like kind of division here, negative 4c divided by negative 4 would also give me c. When I think about 4, negative 4 times what would give me 4? That's still a number. That number is actually negative 1. So I would need negative 4 times negative 1 to give me a positive 4. So if I look here, I would do 4 divided by negative 4, and you can see how that other term would be negative 1. So how I rewrite it would be my GCF on the outside, negative 4. So that's my height times c minus 1. So again, because my second term was negative, I'm showing subtracting 1. Third example, negative 28a, and then my other area is 8. So looking at common factors of 28 and 8. So I might start with 8, right? Maybe I just brainstorm like 1, 2, 4, 8. Okay, 8 doesn't go into 28, but 4 does. So any way you want to think about the greatest common factor, if you need to list them, just kind of off to the side, whatever helps. So 4 is going to be the greatest common factor, but it's going to be negative 4 because my leading term is negative. So then again, negative 4 times what would give me negative 28? That would be 7a. So negative 4 times 7a would give me negative 28. And then negative 4 times what would give me 8? I would need this to be negative 2 in order to have a positive 8. So negative 4 times negative 2 would be 8. So how I write that is negative 4 times 7a minus 2. You can also, if you think about not using the area model, so once you find your GCF, just divide each term by the GCF. And negative 28 divided by negative 4 is 7a. 8 divided by negative 4 is negative 2. So you can kind of see it that way too. That can also help you keeping your positive and negative signs kind of straight. So let's look at our last example. We have negative 16y plus 9. So looking at common factors of 16 and 9, you might realize that you might be thinking like there isn't one. I have 1, 3, and 9 for 9. For 16, I have 1, 2, 4, 8, 16. Now, careful. So factoring a 1 doesn't change a problem. Factoring a positive 1, I should say, doesn't change the problem. Factoring a negative 1 definitely would change the problem. So in this problem, negative 1 is still a factor because it still changes what the other factor would be. So when I take out a negative 1, my other terms are going to actually kind of flip signs, meaning that negative 1 times what would give me negative 16y? That would be positive 16y. And then negative 1 times negative 9 would give me positive 9. So when I go to write my expression, my GCF would be negative 1 times 16y minus 9. Now, if you remember in my expanding expressions lesson, you don't necessarily need the 1 there. You can also just write like subtracting this whole term. So taking out a negative sign or like factoring out a negative 1 is actually still factoring because it's changing the signs inside your parentheses. So these examples, I always pick my examples on purpose to kind of show a little bit of the different ways of thinking about it, showing different examples, right? When you're taking out a one, when you're taking out a negative, a positive, trying to really showcase the different types of problems you can run into. So if you scroll down, there is 4 you do problems at the bottom of the page. Please take your time when you're working on these. Don't forget to double check the sign of your terms. Don't forget to keep the sign with your term. Remember, when you are factoring, you are given the area of the rectangle and you're trying to work backwards to find the dimensions of the rectangle. So what is that shared height or the greatest common factor? And then what are the other widths to get that total width? And you're rewriting it as a product of that height or that length times the total width. So take your time. Be sure to check with your teachers for the answers. And thanks so much for listening and watching. And I wish you the best of luck.